What we have accomplished so far is just we made sure we understand what we mean when we talk about methods in simulation modeling, discrete events, system dynamics. We have built two models using one tool. One was system dynamics model of a new product diffusion, and another one was a simple model of a bank over here. We talked a little bit about optimization with OptQuest, a module, third-party module built into AnyLogic software. We didn't do calibration, but I assume as long as you're simulation professionals, you roughly know how it's done. Basically use the same thing, the optimizer, to do calibration. And now we're at the beginning of part 2, and all we're going to talk about is multi-method modeling and agent-based modeling. Because we haven't built any agent-based models yet, we will build them in this part and integrate them with discrete event models. Okay, so I'll go to the presentations in part 2. So, why multi-method modeling? It's good when you're given the real system that you are to model. It's good when you know what you're going to do. Okay, this is clearly a process. I will build a process-centric model. Here are my resources. Here are my shifts. Here are the parameters I want to vary. These are the places where I expect bottlenecks, etc. It's also good when your system dynamics modeler and the problem you're dealing with is well suited, let's say, for well fits with the system dynamics method. What if you don't know? You're dealing with a problem as a modeler, and you're not really sure this model falls into, let's say, system dynamics or discrete event or agent-based methodology. It's good then when you can try one method, start building model. Let's say start building very abstract model using SD methodology, and then as the project goes on, you see, okay, this is not enough level of details. I need to be more detailed. I need to, at least in the parts of my model, I need to model individual objects, processes maybe, and then you shift down. You build maybe a discrete event model instead of your first system dynamics sketch, or maybe you combine them together. So obvious reasons are, first of all, you may not know in the beginning which methodology is best suited for the problem you're solving. Reason number 2 is that the problem may call for 2 or maybe 3 methods together. Well, our point is that if you're using a single method tool, like discrete event tool, the tool forces you to think single method. You're trying to map everything to the process or everything to a stock and flow diagram, which may not be good for your project. So it's better if you as a modeler know multiple methodologies, and if you have a tool that supports all of them within one framework, then it's not a guarantee, but it still enables you to build to choose the right constructs of the modeling language that fit the problem in the best way. This is the current picture with the tools that you have in market. Very few system dynamics tools. Probably I can add a couple, but not more here. Very strictly defined modeling language. Interoperability, very good. Imports and exports from one tool to another, including AnyLogic. AnyLogic can import Vensim models. a lot of tools in discrete event domain or methods, zero interoperability, no converters from like arena to extensive and vice versa, dialects, not standard language, but methodology is the same. Well, this is engineering world. We're not going to touch it. Here in agent-based modeling, AnyLogic is to date the only professional tool for agent-based modeling, but also you have some open source stuff like Swarm and Repast. These are more coding here, graphical interface here, but these are more suitable for, let's say, toy models. But again, each tool supports just one modeling language. This is just an illustration of what I just explained. Variety of problems. If you're an arena modeler, you will try to map all of them into the process. If you're a power sim user, you will try to map everything to stocks and flows and arrays. If you're a repast expert, you will try to model everything as agents in repast. This is much better way, of course, but it calls for not only the tool is out there, but also the multi-method mindedness or skills. So that was actually the main idea behind AnyLogic, to provide the platform for multi-method modeling. And as such tool, AnyLogic supports multiple languages. Just let's once again go through them. Stock and flow diagrams used for system dynamics. Stocks, flows, variables, feedback loops. Visual language. Language of state charts. We haven't touched that yet. By the way, anybody is familiar with state charts? One, okay. This is the most used language for defining behavior of agents. State information, transitions, timing, reaction to external events. This is very well expressed with the state charts. We're going to be using state chart during our agent-based exercise. Action charts. We haven't touched that either, but the idea behind them is, if you're not comfortable with writing Java code for your algorithmic part of your model, you can use visual language of action charts to define your algorithms. So this is like loop, this is decision block, action block, etc. This is a kind of replacement for Java function. Just letting you know that it's in there. And process flowchart blocks and process flowchart language for discrete event modeling. These are languages, visual languages supported by AnyLogic. Plus, you have Java. Again, in AnyLogic, no scripting language, but AnyLogic is full of what we call extension points, like action of event. You remember I changed the parameter value in the action of event. Entry, exit action of a state chart state. Action when an entity exits the flowchart block, like service or delay. These are all small portions of Java code. You don't need to be Java or object-oriented developer to use this, but you need to understand the syntax of Java if you want to use Java in your model, and simple things like how to write if then else, how to call a function, how to write arguments of a function. These are simple things that is good to know, especially when you do agent-based modeling. These are architectures that you can build with AnyLogic. Just some examples. Pure agents, pure SD, pure discrete event. Then agents in system dynamics environments. System dynamics, for example, models how the city infrastructure develops. I don't know, jobs, housing, taxes, etc. Agents are people. Okay, these are your clients and this is your service system. Clients periodically generate requests and your service system responds. And clients remember the quality of response. Just another example. Etc., etc., etc. These are interesting examples. Inside agents, you can use like system dynamics for in this case. Here, system dynamics is not used as a strategic level modeling tool, but system dynamics is used to describe how decisions are made in people's minds. And people do build models like that, especially people who do, let's say, consumer market analysis or maybe HR dynamics. Supply chain. Agents are supply chain elements. Process is inside agents, etc., etc. So this is infinite, really, number of architectures you can build with AnyLogic. This example I'm not going to build in front of you, but I'll show you how it's built. Discrete event part of the model. Supply chain. Supply, delivery, production, product stock. Or you can treat it as actually retailer stock. System dynamics. This is interesting. This part of the model models the demand for the product, that's the dynamics of this demand. And this part models supply, purely discrete, purely continuous. It's very, looks very close to the model that we built, the product diffusion model, potential users and users. But in the middle we have the demand stock. All the word of mouth and advertising generates not the users, but the demand. These are people who want to buy, but they may not be able to buy because the product may not be available. And this transition from demand to the user, this is the transition of purchasing the product. And it depends on whether the product is available in the stock. Okay? So in the model, I'll briefly show you now the arrival of the product to this queue on the discrete side will generate a unit jumping from the demand stock to the user stock. Does that make sense? I mean the architecture. More or less. Okay. The model looks like this. So supply chain and market model. By the way, all these models can be found here. Models from the big book of AnyLogic. Multimethod modeling. And these are all these example models. So look, the system dynamics diagram where with the two stocks there is no SD flow between the stocks. Nothing. They're disconnected. On the other hand, there is no sync block in the discrete event model. The process ends with the queue block. Okay? And it is the sales event that links this guy and these two. So what goes on here is that this is a kind of pretty regular supply chain. Q has no block after it, but the sales guy is this is the interface. Look at this expression. The inventory policy is something different, okay, look at this. When demand is greater than 1, so if we have at least one person who wants to buy the product, and production stock size is greater than 1, and production stock is, product stock is this Q. So this is a condition on two models, this model and this model. Am I making sense here? Okay. Then what we do, we execute sale of a product unit. We remove the first product from this stock. We subtract 1 unit from demand, and we add 1 unit to the users. And this is the link between SD and discrete event. The rest is apply inventory policy. Well, inventory, we have reorder point and we have order quantity, and basically we inject as many items to the supply source block as our inventory policy gives us. But this is kind of standard thing for any supply chain models. And this is the interface. Let's basically run this model. You see that the demand block jumps up and down, and this is because the system dynamics model is linked to discrete event model. And on this graph, I'll just let it execute up to the end. Okay, these color things are the inventory. Supplier stock, in delivery, raw material in production, and in stock. You see that the pattern of the supply chain dynamics changes over time. And it changes as the market gets saturated. Because after the market gets saturated, the only sales you have are because of product discards. So the people are, yes?
I have a question. In the beginning of your presentation, part 1, you said that supply chain restricts itself.
Supply chain what? Restricts or
itself. What kind of parameters, variable you build for this?
In this case, yeah. These are
the link between this and the first part, and how you can be adaptable for the consumer.
Restructures itself. Yes, that was a different supply chain. There were like multiple producers multiple suppliers, one producer, and the producer was able to choose from who to order. That was a different supply chain, a different model. And this supply chain is very, very simple, straightforward. The only parameters...
That change may occur at any time. So...
in this supply chain, the only parameters we have are the reorder point. So the inventory falls below a certain level, and then we order certain quantity. These are the two parameters. So that's how the supply chain controls itself. Okay, this is the inventory policy. But the supply chain is not the isolated thing in this model. It works for the market. This is the market, the system dynamics model. Demand is generated here, and they work together. So here, the demand stock, this thing, this red curve, when it's up, it means that the demand is not satisfied by the supply chain. Supply chain tries high. You see that these frequent orders, but it's just not capable of satisfying the demand. But as the market gets saturated, the demand goes down, and then the supply chain works in a pretty relaxed way. So it can it can satisfy, and the demand is actually close to zero. Okay, so different aspects of the integrated system, market and supply chain, are modeled with two different methodologies: system dynamics and discrete event. Any questions on this model? Yes.
So here we consider that the main problem is a dynamic system, and then inside we have an agent.
No, there are no agents here. The discrete event part is this process flowchart. And it's a kind of very primitive process flowchart that you would find in any simplified supply chain model.
So my question, if we inverse the process that we produce in function of the demand,
of course we can do that, of course.
Does it change the structure of...
No. In a way, here the order amount depends on the here no, it only depends on the value of the stock, the reorder point. Correct. But what we could do, we could link the demand stock to the ordering. Is that what you... Yeah, okay, so of course you can do that. Yeah. Mm-hmm.
Yes. How is the link between the two types of time?
You don't need to think about it. AnyLogic takes care of that. AnyLogic simulation engine has hybrid time model. So you have numeric solver that takes care of continuous time, and that continuous time is interrupted by discrete events. And AnyLogic is set up to handle let's say, integration well. So you just, define, you don't need, as a modeler, you don't need to think about time. You only need to, of course, to make sure your time units are, let's say, same in discrete event model and in system dynamics, like days or minutes. That's the only thing you should take care. You should take care as a modeler. Everything else is handled. Okay. Now. Example 2. So that was supply chain and market. This example, I'm going to build in front of you. So that is an agent-based model. Its example is from a healthcare area, but you can use your imagination to expand it to any kind of any other application area, because this is a link between agent-based model and discrete event model. So we're modeling epidemic in a certain region. People are susceptible to a certain disease. The disease has immunity periods, so you don't discover symptoms immediately. Once you discover symptoms, you request treatment, and also you reduce your contact rate. Treatment is done by a clinic, but the clinic has finite capacity, and the clinic will be modeled as a discrete event process flowchart. So this is the problem definition. These are some parameters, and I'm going to start building this model. And this is the first agent-based model that we're going to build today from scratch. Oops. So I have my main object. This is where my agents are going to live. And I will create agents using agent population object or wizard. So The agent class is going to be have a name patient. Population is patients. How many? 2,000 people. 2,000 people. Just for visual purposes, I will have rectangular space for the agents. Okay, that's it. So this wizard created for me a collection of agents, environment where agents live, types of space, network, etc. And you can see in the model tree there is another object, patient. I have two editors now, one for main, one for the patient. These are internals of my agent, patient. So far, the only thing I have here is the animation of the person shape. No behavior, nothing. If I run this model, I will have just a rectangular space filled with people doing nothing. I can look at each individual person, number 0, number 1, etc. So they're here, but there's no dynamics in this model. To make sure I have my window maximized always, I'll click this maximize size for my experiment window. Simulation, window tab, maximize size. Okay, so let's start defining behavior of a patient. This is the first time I will use state charts. State charts are coming from software computer science area. They are extremely useful formalism for defining agent behaviors. State chart tab in AnyLogic palette. My patient initially is not sick, but can be infected. Susceptible state. If the person gets infected, the terminology in epidemiology is, we say it is exposed. After the incubation period, we'll say infected, discovers symptoms. This is the initial state. Initially, everybody is susceptible. These are the two transitions. Transition from susceptible to exposed. The only reason is that someone infects you. So we will say the only reason for changing this state. So this transition is triggered by message. And the message is, we will use just a simple string infection. And we will call this transition infection. From exposed to infected is the incubation period. The duration of the incubation period is, according to our problem definition, uniformly distributed between 1.5 and 6 days. So this is timeout, uniform 6. And then you are infected. After having been infected, you have two options according to our problem definition. Option 1, you can die. Option 2, you can cure and become immune. So I will create a state recovered. And I will create a final state, dead. I'll use a branch here. So far there is no clinic, no treatment in our model. So the only way of exiting the infected state is when the illness naturally finishes. And this is again illness duration if not treated from 10 to 40 days. Sorry, here, timeout, uniform, from 10 to 40 days. What is the probability of survival? If the person is not treated, still 90% of people survive. So here, with this branch of transition, we will say the condition is random true 0.9. And this is the default exit. So if this condition is false, then with a 10% probability the person will die. What transition is missing here? The immunity is not forever. The immunity will be lost after a while, right? And therefore, from 30 to 120 days, exactly, the person will go back from here to there and will become susceptible again. So this is immunity lost. And this is symptoms, end of incubation period. And this is illness finishes and the person is not treated. I will simply say not treated. Okay. Connector. Okay. We can run this model, but before I do it, I'll do some animation of my agent-based my agents. So I'll leave. Okay, susceptible will be green. Exposed will be, let's say, orange. Infected will be red, and recovered will be. What? Okay, sky blue. Second.
The infection is due to a message.
Yes, but so far nobody's sending them in. That's a good point. Again, you're you're slightly ahead of me. Okay, I will draw. I will paint the person according to the states. So the person shape has name person. So here I will say person. Set fill color. What was it? Yellow-green. So once again, I'm using the simple Java insertions to program interaction between the, in this case, animation and the logic. So I'll copy this and use in the other states as well. Orange. This is orange red. And this is, what is it? Light sky blue, I think, yes. Okay. Dead. What are we going to do with dead people? We're going to remove them from the model so they do not interfere with people who are still alive. I mean, interfere at least visually. In agent-based modeling tools, you are able to create and destroy agents dynamically. So my agents live here in main. So what I'll do, I'll say, main remove patients. This means me. I'm dead. That is it. If I run this model, everybody is in susceptible state. We can look inside every single person. This guy is this current state susceptible. Number 3, 4, or number, I don't know, 1207. They're all in susceptible state. Nothing is happening in the model. Why?
You need patient 0 and translation.
Yeah, because we need initial infection to be injected into the model. Let's do that. According to our problem definition, initially 5 people are infected. So let's do it. In the main, I have the startup code. This is the action that is executed on the model startup. So what I'll do, I could write 5 times one statement, but I'll use the simple Java for loop instead. Patients, random, receive, and the message that triggers infection is the string infection. Okay? I'm running the model. See that there are some people who are sick, but they are not spreading infection around, right? Because we haven't yet programmed that. So our next step is to, now they're going to just, recover, and still there will be nothing else in the model. Now let's program communication between the people. People communicate all the time, but we're only interested in communication between people who carry infection and the others. Therefore, we will only define this communication in the 2 states. In which states? Exposed and infected. In both states, the person is infectious, but the difference is that before you discover symptoms, you are actively contacting other people. After you discover symptoms, you're less frequently contacting other people. So, contacts is some activity which goes on inside the state. We call it internal transition. And let's look at how frequent it is. Normal contact rate, 5 people per day. Infection probability is 7%. So here I'm writing with the rate of 5 per day, I contact other people, and people get infected with probability of 7%. I simply can say that I could model all the contacts, but I do a simple optimization here and model only those contacts that result in infection being passed. So I'll multiply 5 with 7%. And the action is contact other person, random person, and pass him infection. So I'll send infection to a random other person. Okay? And I'll copy this to here. And the difference is that while you are sick and know that you're sick, you only contact one person per day. So this is 1. Let's run the model again. You see that epidemic never ends, and I'll draw some charts in front of you in a second, and you will see why. And people, yeah, will soon be out of population, out of people in this model. Oh no, some remained, and okay, 6 people remained, and they are obviously in susceptible state. Okay. Just for fun, I'll do one more thing. I will say that we have in this area, in this rectangular area, people only contact others within a certain range. And this is kind of normal things that you do in agent-based modeling if you want. So I'll say that my agents are linked in a network which is distance-based, and the connection range is 30 whatever kilometers. And in the patient, that was environment object. And in the patient, I will say that I'm not contacting random person, but random connected. Okay, we see roughly what's happening in this model, but it's better to collect some statistics on how many people are sick, how many people are infected, etc. For that, in AnyLogic you use statistics over agent populations tool. So agent population is here, and we add statistics. Let's see, number susceptible. Count all people who satisfy this condition. State chart. Active state is susceptible. This is defined in the state chart. Item means current person. And we will copy this for all others. Exposed, and this is exposed. Infected. And finally, recovered. This is inevitable that in agent-based models you need periodically to loop through the agents to collect statistics on them, because this is clearly an individual-based model. And I'll bring the I'll use time stack chart to display what goes on. And patients exposed, and this again will be this way. This is a bit routine, but it's inevitable in this case. Oh, sorry, this is yeah, susceptible, and this thing goes here, and here I want susceptible. So this is, and then another two items is infected. This is red, and the last one is this is the title, and this is the actual data recovered, and this is light sky blue, and I want it to be displayed over the period of, let's say, 2 years, well, 500 days. Okay. It goes this way. Okay. Yeah, I know something is wrong in my model. And what's wrong is that the immunity period is almost, yeah, because the population was reducing very rapidly. So, and I know how it should be, so I'm lucky. So I forgot to specify the immunity period, which is from 30 to 120 days. And you were watching me, you should have told me about this.
Is there some debug mode?
Huh? Huh?
Is there some debug mode?
Yeah, of course, yes.
And you can watch...
You can go event by event, for example, or you can specify breakpoints in your model, so you can stop. So from 30 to 100 days, let's run with the immunity period. This is more interesting. Yeah, I will adjust the vertical scale of the chart a little bit so it's nicer. So the vertical scale of the chart is fixed to initial total population. This is the time scale control. So, can somebody tell me, why do we have several waves of the population? Why doesn't it come to its end after the first wave? this happens simply because by the time the last person in the first wave got recovered or became dead or died, there are already people who lost immunity. And so those people from the previous wave, they infect people who are already not immune, already susceptible. And therefore, the disease, the epidemic will go in these waves for a large period of time. That's it. And then it gets... Okay, so by the way, what we did, we just built an agent-based model. This is a classic example of the agent-based model, where we have individual objects. This model is very individual-centric. Behavior is defined at individual level. Just to make sure we understand what is a state chart and how it's different to a process flow chart or system dynamics stock and flow diagram. First of all, this state chart describes states of one particular object. The states are mutually exclusive. The person is either susceptible or exposed or infected or recovered or dead. It cannot be in two states simultaneously. Unlike in process flowchart, where there can be multiple entities in one block and multiple entities in another block, here you can think of the state chart as of the chart where just one token, current state, and it travels from one state to another, jumps from one state to another. Transitions in the state chart are associated with events, and events can be like here. Message arrival. The message infection arrives to this state chart. Here, timeout. The person spends a certain time in the exposed state and then exits. Again timeout. And again timeout. Here, this transition is periodically executed with at a certain rate. Rate means exponential inter-arrival time, exponentially distributed timeout, so to say. Okay, this is pure pure agent-based. Any questions on this part?
Yes.
No. You first.
Agent-based simulation. Usually, the word agent is to explain that each individual has a certain knowledge. It can be for himself and collective knowledge. A state chart is part of a specific way to describe knowledge.
One of the ways, yes, absolutely,
situations.
Absolutely.
What are the other possibilities that you offer to incorporate other types of knowledge?
Okay, I'll make a comment on the first statement. Agents can be very different. Agents can be smart, intellectual, adaptive, or agent can be simple, let's say dumb, reactive, passive. Like here, agents is pretty simple, very simple behavior, fixed, let's say. The only variability is stochastic, right? Because we have stochastic, durations of stay in different states, right? Like here and here. Well, stochastic probability, 90% of probability going here. Now, how else can you fill your agents inside, right? Anything. For example, you can, because agents is not different from any object in the model. So what you can do, system dynamics. You can put in some stocks and flows and define feedback loops, whatever, and you can say, okay, this is how my agent, for example, makes decisions. This is what impacts. Maybe my perception of, I don't know, Pepsi Cola and my perception of Coca-Cola have certain dynamics, and once they, the threshold is this big, I switch my favorite product, something like that. You can have processes inside the agents. Typically, this wouldn't be people. This could be, I don't know, elements of supply chain, producers, companies, whatever. So, and you can do action charts, pieces of code.
Is it possible to have BDI agents?
To what? To?
BDI agents. Belief, desire, intentions.
Yeah, of course, but this is up to you how to program the actual decision making. We're providing languages. So these are the main languages of AnyLogic: state charts, system dynamics, process flow charts, action charts. The actual, let's see, rules when things happen, it's up to you how you design that. Let's say purchase decisions when you model consumer markets, right? Or in, let's say, even in healthcare, we could implement here the, and we will be implementing in a second, the patient's decision to request treatments. In our case, it will be unconditional. I discover symptoms, I request treatment. In your case, it could be conditional, based on previous experience, based on his, let's say, trust in the healthcare system, income, insurance, whatsoever. So we provide the elements for the logic. You program the logic. So.
But for programming this, you will use Java.
No.
You don't provide any structure for doing this.
No, because state chart is one way. Yeah. Okay. It could be state chart. It could be action chart with I don't know, like while loops, etc. So many different ways, including Java. You can do it in Java. So that's that is the what you can put inside agents, and in this respect, this is the richest tool for the agent behavior definition that is out there. If you think of agents as of simple things like cellular automata, where decision is, I don't know, how to in which cell to move, etc. Then you could use discrete states and cellular automata support that we have in AnyLogic. But these models are pretty normally of, let's say, have limited applicability. The real, I mean, industrial level agent-based models, they're full of, they're full of these things, they're full of that things, sometimes action charts. Okay, any, yeah?
State chart is the behavior of one agent.
Behavior decision.
Behavior. Is it possible for an agent to have multiple state charts?
Yes, many state charts. So you can.
And you can execute them in parallel.
And they will be executed in parallel. Yes, that's true. So you can do another state chart here, and for example, this describes the state of a person with respect to disease. And this describes the state of the person, for example, with respect to having health insurance or not having health insurance, or whatever, work-home pattern, whatever. So yes, you can do that. Yes.
This is the old agent's behavior. What if, for example, I want to model a negotiation process between two agents?
Mm-hmm.
How do you handle this? Because
interaction?
Yes, it's a kind of interaction.
Interaction. Again, many different ways. Actually, here you already have interaction. A person contacts other person.
Yes, based on the proximity.
Based on the proximity. It could be, you could have fixed relationship, like, for example, colleague or child, father, and you can remember your for example, kids or parents within the agent and contact them in a special way, etc. So it's actually unlimited. You can call functions directly between agents. You can send messages.
Is there a way to express the interaction protocol?
To express what?
The interaction protocol, the negotiation process. Is there a way to express it explicitly, or is it distributed in the different behaviors of the agent?
It will be it will be distributed. Yes. So like.
There is no way to express it.
So if your question is whether we do provide a view like a message sequence diagram, no, we don't provide it automatically, but we'll use it a lot when on paper when designing agent-based models. So I treat message sequence diagram as not as, let's say, tool view, but as a kind of design phase paper view on things.
And you don't have these tools for designing the model? You just use paper for now?
Yeah, for message sequence diagram, yeah, because it's typically very simple. It's supported here in, for example, state charts, because the order of states and messages gives you the order of interaction. But we don't find it really useful to support it as a tool view on an agent-based model. Okay. More questions on this? No. Okay. I think we'd better continue with what I wanted to accomplish. So I'll delete all the extra stuff here. Make sure it compiles. And now I will implement the missing transition. That is transition from infected to recovered, and I'll call it treated. So if the person requests treatment and if he manages to be treated in a clinic, then according to our problem definition, he recovers for sure, unconditionally. And that transition will be obviously triggered by some external system, by a clinic. So I'll say here a message. It's triggered by a message. Treated. Let's build the model of a clinic. I'll build it at the main level. So I have main is the kind of global level, or let's say the main object where everything else is happening. And we have patients living inside main. Now, right now I'm in main. And I will create this kind of flow chart. Okay, enter. Q. Weight treatment. Delay. In clinic. And then sync. discharged from the clinic. Okay, the parameters. Bed capacity is, we have 20 beds in the clinic, and the treatment is deterministically 7 days. So, treatment, the capacity of the delay is 20, and the delay time is unconditionally 7. And we will just put the maximum capacity for the queue. Now let's link the model. How do we link patients and this flowchart? We will let patients inject entities into the flowchart. We will call these entities treatment request. And when the patient is being discharged from the hospital, they will just let the agent know. They will send the message treated. So the first thing, I'll probably have a slide for that. That's the slide. That's what we're going to do now. So when the person discovers symptoms, he will inject an entity into the flowchart, and that entity will carry let's say, the reference to the patient. When the person gets treated, he will, here in sync, he will notify the agent by sending him the message treated, which will trigger the transition. This is a very simple link between the two modeling paradigms here. So, the only, let's say, extra thing you need here is the treatment request that will carry the reference to the person. So I'll say new treatment request, new entity type, and it will have just one field, patient of type patient. Finish. I don't need any Java code here. So I'll go to the patient now, and I go to the symptoms. I discover symptoms, I request treatment. So we're in the transition symptoms, and here I will write. The clinic is at the upper level in main, so I say main, enter. This is the first object in the enter, first object in the flowchart. Take new treatment request parameterized by myself. Oh, sorry. This. So I request treatment. Then this part of the interface is ready, and we need to notify the agent when he is treated. This is done in main when the person is discharged. I say that the entity class here is treatment request, and what I do, clinic is full and there's huge queue of people waiting to be treated. Let's see how this affects the dynamics of not much really. Yes?
Don't we have to precise the probability for choosing, making the decision to have a treatment or not?
We could, but in this simple example I decided to make it unconditional, but you could, of course. So here you could say, for example, sorry. Like this. So now only 50% of the people randomly will request treatment. Okay, but I'll...
What happens if, please show me the diagram.
Which diagram? This diagram?
No, no,
Stage up.
the other one, the stage up. Yeah. What happens if
If you die, why?
Yeah, that's an excellent question, because if you die,
what happens if you die while you are in the
while you are in the clinic? That's That's exactly in the decently built model. You need to remove the entity from the clinic, right? The dead body from the clinic. And indeed, we'll do that in a second. So I'll remove this random true. I will increase the capacity. Or actually, I will put in the control here. With a clinic of 20 people, with a clinic of 200 beds, the epidemic is cut off at the first wave, as you can see. Another experiment.
Can you do replications? Can you replicate, because you use probability in each case, and what happens to the chart, to the curves, if you use replications?
Certainly you can do it, because agent-based model is no different from any other type of model, and
it just means that you cannot use the curves. That's it. Doesn't it?
You can use different kinds of curves. Then
if you use replications, you have
you would use I would say two-dimensional histogram instead of deterministic curves, of course.
If you have 30 replications, you cannot have 30 curves, can you?
You can. It depends on how well you can display them.
In this case, you could, for example, display the average.
AnyLogic has two-dimensional histogram, which is suited exactly for that type of graphs. Yeah, so that's basically it with the model. In the full model that you have in your in AnyLogic, you have where is it?
Can you optimize a parameter that is in an agent that is used in a state chart using that request?
Yes, of course you can, because
for example, number of beds is in the discrete event part. But if you had another parameter that would be inside.
Yeah, if you have parameters inside agents, then there's a number of ways you can.
Yes, you can.
You can. It depends on how big is your parameter space, because when you optimize over, let's say, 100 parameters, then typical OptQuest would do nothing, and no general purpose optimizer would do anything useful with that many parameters. Okay, but what I wanted to show you that this is the full model which you have in your software. Same thing, but you have this cancel treatment request function, which is called when the patient is not treated, and it removes entities from the clinic. And behavior is slightly different, of course. This is with 20 beds.
And I guess it's possible also to model the moves of the agents?
Yes, absolutely. Okay, let's see where we are. How much time do we have now?
5 minutes.
5 minutes. Okay. So one thing I wanted to show is this. Yeah.
A lot of people who have
Trains.
are already
Leaving.
leaving, so you have 10 or 15 minutes.
Okay.
To close.
Okay. One feature I wanted to show you definitely is this, is you can export your model to Java applet, and that means it is readily available for publishing on the web, or Java application. In this case, it's available for building into bigger applications, exporting or putting on any Java-enabled machine, etc. So what I'll do, we also have runthemodel.com, which is a free portal for which hosts AnyLogic models. But I'm not connected to the internet at the moment. So what I'll do, I'll export into an applet and show you that the model runs in the browser. So this is security settings. No, my security settings have blocked local applications from running. Sorry about this, but I should have tested this. But the bottom line here is that the model is pure Java. As being pure Java, it can run anywhere, and it is completely independent on the model editor, the environment. And you can publish it and let other people run it in their browsers without installing AnyLogic software.
Do you have versions for Unix environments?
Yes, it runs on Mac, Linux, and Windows, of course. It's cross-platform, the whole thing, the editor and the model.